Hello everybody and welcome back to PharmaWise. As promised in the last video, today we will be discussing problems related to solubility and solubility product. In the last video we have discussed the concept of solubility and solubility product, and now we are actually going to solve some of the examples, and we will learn how to figure out the relationship between solubility and solubility product in problems, numericals. Okay, so before starting with the numericals, first things first, let's briefly go through what is a solubility first. So solubility is nothing but amount of solute dissolved in a given amount of or unit volume of solvent. So it is expressed in gram per liter. So basically when I say the solubility of NaCl in water is say 30 grams per liter, for example, then it means in 1 liter of water 30 grams of solute has been dissolved. So that is the solubility. Now what is solubility product? We have already discussed it, but still solubility product is given by Ksp, and it is nothing but the ionic concentration of that particular salt at a saturated point or in or at solubility equilibrium, whatever you call it. So ionic product at saturation or ionic product at solubility equilibrium is referred as Ksp. Now next point we have to consider is you must be knowing molar solubility, how to calculate number of moles from the solubility. So molar solubility is nothing but the solubility in gram per liter, which we have already derived, solubility in gram per liter, which might be given in the problem, and divided by molar mass. So whenever we divide the mass of substance in grams by its molar mass in gram per mole, it gives us number of moles in that particular volume, which is referred as molar solubility. So we have seen what is solubility. It is expressed in gram per liter. Molar solubility, we have to just divide the solubility in gram per liter by the molar mass of that particular salt, and we'll get the value of molar solubility in mole per liter. The unit is going to be mole per liter. And then we have seen how the Ksp is derived. Ksp is written based on the law of mass action. Yes, so we have to consider the law of mass action here. Suppose I have this equation, A moles of A react with B moles of B, and they are in equilibrium with C moles of C plus D moles of D. If this is the condition, how I am going to write the law of mass action? K is equal to product of concentration of C raised to C, concentration of D raised to D, means product of concentration of products raised to their coefficients and stoichiometric coefficients, and here in the denominator we will have concentration of A raised to A, concentration of B raised to B. If you are not sure how to write the law of mass action, I have an entire dedicated video on it. I will link it in the description or in the I button somewhere here. But basically it is very simple. What we have to do is we have to write the concentrations of individual species, and if that species is in more number of moles, like say there is some stoichiometric coefficient like 2, 3, then we will raise that to that power. So this is how we are going to write the law of mass action. Now with this basic introduction, I hope all of you are on the same page with me, and now we'll start with actual solving some problems. So let me take the first problem. I have shortlisted some problems for you. So we'll start with first problem. Calculate the Ksp of magnesium carbonate. So what I have to calculate is Ksp of magnesium carbonate. I have to find it. If 1 liter of its saturated solution contains 0.533 grams of magnesium carbonate at 20 degrees Celsius. So 1 liter in 1 liter at 20 degrees Celsius. This is my given information, that at 20 degrees Celsius means at particular temperature my magnesium carbonate is dissolved. This much grams are dissolved in 1 liter of solution. Now in saturated solution, so basically what they have given us, they have given us solubility in gram per liter, right? So how many grams? 0.533 grams in 1 liter. So this is nothing but my solubility in gram per liter. Now what they have asked us to find, KSP, means solubility product. So what we have to do first we have to figure out the molar solubility from the solubility in gram per liter. So how I am going to do it? Molar solubility, I have just given you the equation how we calculate molar solubility. The solubility in gram per liter, which we are already having, and we will divide it with the molar mass of that particular solute. Now our solute is magnesium carbonate. Now the molar mass of magnesium carbonate is given, and it is 84.32. It is always gram per mole. So if it is given, I have the solubility, I can easily find out my molar solubility. So it will be like this, 84.32 gram per mole. If I solve this, it comes, you can solve it, but I have already solved it for you. So it comes 0.00632 gram, no, it's molar solubility na, so it's mole per liter. Now I will write this in scientific notation. It comes 6.32 into 10 raised to minus 3 mole per liter. Now what does this molar solubility is telling me? I'll tell you. I have magnesium carbonate. So magnesium carbonate, when I will dissolve, it is going to give me ions like Mg++ ions and CO3- ions. It's magnesium ions and carbonate ions. Now whenever I will dissolve these many moles of magnesium carbonate, they are going to yield same number of moles for magnesium and same number of moles for carbonate ions. So if I say that I am dissolving 6.32 into 10 raised to minus 3 mole per liter of magnesium carbonate, it means simultaneously when it is getting dissolved, 6.32 into 10 raised to minus 3 mole per liter will be the concentration of Mg++ ions, and same 6.32 into 10 raised to minus 3 mole per liter will be the concentration of CO3- ions. Now in the next step what we will do, we will try to write the equation for KSP based on the law of mass action. I am having this equation with me. Now this magnesium carbonate is solid and these are aqueous ions. So how I will write the law of mass action? See, there are no stoichiometric coefficients. 1 mole of salt is producing 1 mole of this cation and 1 mole of this anion. So it's very simple. I will just write Mg++ into CO3 minus. Now you must be wondering why I have not considered this at the denominator, because the concentration of solid magnesium carbonate is constant, and that constant we have already considered while we have designed this constant KSP. You please go through the last video if you are not sure about this, okay? But we will write the KSP equation like this. Now I have the values, so I will directly put the values. 6.32 into 10 raised to minus 3 into 6.32 into 10 raised to minus 3. So you just have to multiply 6.32 into 6.32, it comes 4, and minus 3 comes minus 6. So 4 into 10 raised to minus 6 will be my KSP value for magnesium carbonate, which I have figured out. So this is how we are going to solve the problems where we have been given the solubility in gram per liter and we have to convert it into KSP. So what we'll do first, gram per liter solubility converted to moles per liter solubility, molar solubility. When you are having molar solubility, you come to know how many moles of cations and anions are being formed. So you basically come to know about the ionic concentrations of ions, and then based on the ionic concentrations and writing the KSP equation, we will figure out the value for KSP for that particular salt. So this is how we are going to do it. Let's move on to the next problem, where we will see how we can actually calculate solubility from Ksp value. So here we have seen solubility is given and Ksp we have to find. Now let's reverse the situation and let's solve a problem where Ksp will be given and we have to figure out the solubility. So the problem is calculate the solubility in gram per liter. Calculate the solubility in gram per liter of calcium sulfate. So calcium sulfate means CaSO4. And Ksp of CaSO4 is given. Ksp for calcium sulfate is given, and it is how much? 2.4 into 10 raised to minus 5. 2.4 into 10 raised to minus 5. This is the value for Ksp. Now they have given us Ksp and they have asked us to figure out the solubility in gram per liter. So what we will do, we will just reverse the sequence of steps which we have performed just now in the previous example. So let's do it. So what we will first do, we will write the equation for calcium sulfate. If I dissolve the solid calcium sulfate, it is going to give me calcium ions plus sulfate ions, right? Ca plus SO4 minus. Now what I will do, I will write the Ksp equation. So Ksp for calcium sulfate will be concentration of calcium ions into concentration of sulfate ions. Now here also we are fortunate that there are no stoichiometric coefficient, otherwise we have to consider the powers, but all right. So this can be the equation for Ksp. Now what they have asked me to find the solubility in gram per liter. I have this equation. I have the value of Ksp given, right? So I can put my value here. 2.4 into 10 raised to minus 5 is equal to this into this, which means this value. Now calcium sulfate equation, you just observe 1 mole of calcium sulfate is giving 1 mole of calcium ions and 1 mole of sulfate ions. So if I consider that concentration of calcium ions is X and concentration of SO4 minus ions is X, then my calcium sulfate Ksp is going to be X square, right? So what I will write here is X square, which is if I solve, so X comes under root. Now see, 2.4 into 10 raised to minus 5. So if I want to take easy under root, I will modify this number as 10 raised to minus 6. So X square is equal to 24 into 10 raised to minus 6. I will do it. So therefore X comes root 24 into 10 raised to minus 3. Now root 24 will come somewhere near 5. So it comes 4.9. 4.9 into 10 raised to minus 3. Now what is this? This is my molar solubility. X is nothing but my molar solubility, right? So this is the molar solubility in mole per liter. It means I have this much concentration of calcium ions, this much concentration of sulfate ions. And if so, I have the Ksp value of this. Now what we have to figure out? Gram per liter solubility. Now I am having molar solubility. So how I will do it? I have the formula that molar solubility is gram per liter solubility divided by molar mass. I have to figure out the gram per liter solubility. So I will just modify that equation and I will write solubility in gram per liter is equal to molar solubility in mole per liter into molar mass in gram per mole. So I have molar solubility 4.9 into 10 raised to minus 3 and molar mass for calcium sulfate, it must be given, it is 136.1. 136.1. So if we solve this, what we'll get? We'll get the answer 6.67 into 10 raised to minus 1 gram per liter. You can solve it if you wish to, but I have already calculated, and it comes 6.67 into 10 raised to minus 1 gram per liter. So just observe what we have done. We want to figure out the solubility in gram per liter for this salt whose KSP is given. Now what is KSP? Ionic product. Now ions are formed in same quantity. So I have taken KSP is equal to x square. X is my molar solubility for this as well as this. Now x value I have figured out, which is molar solubility. It means these many ions for calcium, these many ions for sulfate has been formed. Now this molar solubility we can easily convert to gram per liter solubility by multiplying it with the molar mass of the salt, and we will get the answer. So this is our solubility in gram per liter. 6.67 into 10 raised to minus 1. So this is how we are going to solve the problems if asked this way. Now one more problem I want to address here, and that is related to conditions of precipitation. In the last video we have seen 3 conditions of precipitation, 3 criteria for precipitation. If the ionic product is equal to the solubility product, then the solution is saturated. Saturated solution. If KIP means ionic product is less than KSP, it means solution is unsaturated. An unsaturated solution has the scope for dissolution of further salt. So here we can actually dissolve more solute in it. But if my ionic product exceeds my solubility product, the solution is supersaturated, and supersaturated solutions tend to precipitate. It will lead to precipitation. So these are the basic criteria which we have discussed. Now let's solve a problem. A solution is prepared by mixing equal volumes of 0.1 molar magnesium chloride and 0.3 molar sodium oxalate Na2C2O4 at 293 Kelvin. Wood magnesium oxalate will precipitate out. Wood magnesium oxalate precipitate out. And KSP of magnesium oxalate is given. KSP of magnesium oxalate is given. It is at the same temperature 293 Kelvin. It is 8.56 into 10 raised to minus 5. Let's solve this. What they have given? They have mixed equal volumes of, this is very important, they have mixed equal volumes of, means if they are having 50 ml of this and they have mixed it with 50 ml of this, what is the total volume? It is 100 ml. So whatever concentration they have given us for these particular salts, it is going to half. It is going to be halved. So how we are going to consider? Magnesium chloride is going to give us magnesium ions, right? And magnesium ions will be formed in 1, means the stoichiometric coefficient will be 1. I will write it for your convenience. Magnesium chloride will give me magnesium ions plus 2 chloride ions, and sodium oxalate will give me 2 sodium ions plus oxalate ion, means Mg++ and C2O4 minus, they are having 1 as the coefficient, so they are not having any coefficient for that matter. So what I am going to tell you is concentration of magnesium ions is 0.1 molar, but now as the volume is doubled, as we have mixed equal volumes of both of them, so the effective concentration of magnesium ions will fall to half of its given value. I hope you are understanding. Suppose I am mixing 50 ml with 50 ml. In this 50 ml, 0.1 molar magnesium ions were there, but now they are floating in the 100 ml volume. So obviously effective concentration drops to half. So 0.1 by 2 comes 0.05 moles. And now let's talk about oxalate ions. Now oxalate ions, the concentration, initial concentration they have given 0.3 molar, but again the volume is doubled, so 0.3 will be halved, so we'll get 0.15 molar. Now I am having concentrations of ions. What I want to figure out whether this salt made by combining these two ions will precipitate or not. So for that I have to consider these criteria, whether the ionic product of these salts is exceeding the solubility product or not. So I will calculate the ionic product. So ionic product will be concentration of magnesium ions into concentration of oxalate ions. Concentration of magnesium ions is 0.05 and concentration of oxalate ion is 0.15. So 15 5 is 75, 1 2 3 4. So this is going to be my KIP value. I will make it 7.5 into 10 raised to minus 3. This is going to be my KIP value. I am already having KSP value for this particular salt, and the KSP value for this salt is 8.56 into 10 raised to minus 5. Now look at both the values. This is minus 3 raised to minus 3, this is raised to minus 5. So KSP is definitely less than KIP. It means KIP is exceeding KSP. It means my solution is already supersaturated, and if the solution is supersaturated, it will definitely precipitate out. So precipitation will definitely occur. This is how we are going to predict whether a particular salt will precipitate out or not based on the comparison between their ionic products and their solubility products based on these criteria. I hope you understood these problems, and I hope now you can solve such kind of problems on your own. If you found the video helpful, do not forget to like the video and share it with your friends, and subscribe to the channel so that my channel can grow. And you please keep studying, please keep learning, and keep watching PharmaWise. I'll see you in the next video. Till then, you take care. Bye bye.